Yes, that'd be great. So yeah, I have the honor of introducing Bartek Czech from Shanghai University, who's going to be talking about holographic complexity from group cohomology. Please take it away.
So thank you very much for the invitation to speak here. Let me first say who are the co-authors of this project, and it's very complicated. This is mostly based on a project in collaboration with Jan de Boer and Lampros Lamprou from Amsterdam and from UBC respectively, and also my students Zizhi Wang and Bowen Chen. Actually, Chen Bowen will be definitely applying for postdocs next year. So this is a heads up for anybody who is looking for postdocs in a related area. But it's also very largely, this talk is also very largely inspired by a parallel project with Gabriel Wang and Robert Rausendorf, who Gabriel Wang is just moving to Harvard, and Robert Rausendorf from Fudan, and Robert Rausendorf is an information theorist at UBC. I also owe great thanks to Janet Hang from Fudan, who explained a lot of things that are in this talk. And so it's actually a mishmash of several projects, and I don't know how the paper writing is going to turn out. All of this is not on the archive yet, so, and also very much in flux. So I welcome any criticism, comments, and suggestions for improvement. So without further ado, this talk is about holographic duality, first of all. And because the symposium is kind of general, let me just say a few words, necessary words about what holography is, and I'll get quickly to the meat of the talk. So we all know that holography is a duality between a theory with gravity and a theory without gravity. A theory with gravity would have anti-de Sitter boundary conditions, and a theory with gravity, without gravity, would be a conformal field theory. And it's conformal because isometries of ADS form a conformal group in one less dimension. And one of the great things about holographic duality is that it allows us to ask as a scientific and not just as a philosophical question, what are space and time made of? And the idea is that they're made of the geometry of information in the dual conformal field theory. So, so this is a theme that's been going on for at least 15 years in holographic duality. And I'm trying to lay one extra brick in this already large wall of connections between information geometry in the CFT and actual geometry that we experience as gravitational beings, but in ADS space. So what are examples of this duality between the geometry of information and geometry on spacetime? Well, the most maybe famous statement would be the statement here, if you can see where I'm pointing with my pointer, between extremal surfaces in ADS and entanglement entropies in the CFT. These would be von Neumann entropies of reduced density matrices of regions. So in case you haven't seen this before, let me just do a lightning review. So we will take a CFT. Well, let's start from ADS. ADS has a set of coordinates which make it look like a cylinder. So we typically draw it as a cylinder, and the solid cylinder is ADS. CFT is in one extra dimension, so it lives in an empty cylinder, and that's here. Now that's including time. Time is vertical. So if I look at an equal time slice of the CFT, this is this region here. And this circle, which is an equal time slice of the CFT, if I divide it into two pieces and call one of them A and the other one A complement, I can form the reduced density matrix on A by taking whatever state I have in the CFT and tracing out the complement, which is A bar. This thing is called the reduced density matrix of A. And now the von Neumann entropy of this guy, S of A, is famously, by the Ryuta-Kayanagi proposal, equal to the area of a surface that I could have drawn through the bulk of ADS that passes through, that is anchored on the borders of A. So this is a statement from 15 years ago, which started this whole current in holography. Now, if we step back a little bit and ask, what about rho A itself? If I just don't take the von Neumann entropy, but the full rho A, what is that? Well, this is also an information theoretic concept. Now, it also has a nice dual in ADS space, and that dual is the entanglement wedge of A. So roughly speaking, it's a region which is bounded by light-like sheets that emanate from this extremal surface S of A. That's not exactly a true statement what I said, but it is approximately true in some circumstances. Suffice it to say that there's some way of defining covariantly a region which is precisely dual to the information contained in row A after I traced out. So I forgot a bar. I retained the information about row A in the CFT. In the bulk, I retained the information about this entanglement wedge. Another thing that we have here is minus the logarithm of row A. This is an operator which I can treat as a Hamiltonian. And if I do, then this is the Hamiltonian with respect to which row A is thermal. It's kind of a tautological statement, but it allows us to define some operator which deserves to be called a Hamiltonian. And this modular Hamiltonian, when I look in the bulk at what it is, it turns out to generate boosts which are orthogonal to this Ryuta-Kayanagi or to this extremal surface, at least close enough to that surface. When I go far away, some corrections kick in, but close enough, I can make this statement correct. And so this is a little table of things that have an information theoretic character on the right-hand side in the CFT. And then on the left-hand side, I have these ADS objects, which are extremely geometric. There's an area of a surface, there's a generator of boosts, which is an approximate Killing symmetry of this geometry. And then there is some subregion that I have defined covariantly. Now, this talk today is about a new entry in the this dictionary, which is about complexity. And roughly speaking, complexity is supposed to be a measure of how big ADS is, or whatever geometric spacetime we're talking about, sideways. So in the spatial extent of it. Now, how would we measure a spatial extent of a geometry? We can talk about a volume of it. That's like the simplest way of saying how big a spacetime is in terms of its spatial extent. Just take the space and see how big it is, that's the volume. Well, a more sophisticated maybe way of quantifying how big a region of spacetime is in terms of space, the spatial extent, is I can take some region and I can find a space-time region, a spatial region, and I can define a space-time region which is the domain of dependence of it. So everything that happens here can be calculated from what happens on an equal time slice here by using equations of motion in ADS. And this domain of dependence, I can also take the volume of it, but now this object also has the right units so that I can talk about the action of it. And the action inside this object is inside this region would be a dimensionless quantity, which is something we can call complexity, perhaps. And the statement that, okay, so here I just described to you two ways of describing or quantifying how big a space-time is in its spatial extent. And the question is, what is that dual to in the CFT? So if this idea that geometry as we experience it, or as we would experience it if we lived in ADS, if that geometry arises from information geometry in the CFT, then there must be something, some quantity in the CFT responsible for that. And what is it? And a famous proposal by Lenny Susskind and collaborators from these years is that this should be the state complexity of the CFT state. Now, what is the motivation for this statement? I'll say a little more, I will say a lot more actually about complexity, but let me just sketch the motivation for why Lenny Susskind said this in the first place. So his motivation was mostly from the physics of black holes. He looked at a black hole, like here I drew a Penrose diagram for a two-sided black hole, and he made the interesting observation that if I look at slices, these are covariantly defined, so maximal volume slices from one side to the other side of this two-sided black hole geometry. And I ask about how they vary with time. So here's one that's a little later. Here's one that's drawn even later, and so on. Then just get larger and larger, and they grow larger and larger for an exponentially long time, linearly in linearly in time. And in fact, this is like a simple one example. But you can make more complicated examples basically by cutting and gluing pieces of this picture in more complicated arrangements. And those more complicated arrangements correspond to sending shock waves through spacetime. And the shock waves would take pieces of this diagram and sort of reglue them together in a translated fashion, in a staggered fashion, so that these equal time slice slices can end up growing arbitrarily large, and they have a specific dependence on the parameters of those shock waves, which in fact generalize this statement here, and which indeed behave like complexity should. Okay, so that's the motivation. The motivation is coming mostly from black holes. In this talk, I will not be talking about black holes, because if the proposal that complexity is measures sizes of geometries is correct, then it can't just be correct for black holes. It has to be correct for arbitrary spacetimes. So I will not actually be talking about black holes, but and I also want to emphasize what my sketch so far has left out, which I think is very important to the story and to the eventual success of this entry of the holographic dictionary, which is I have been extremely vague so far about what complexity actually means. So far, I just used it as a word, and I said, oh, volume or maybe action in this region called the Wheeler-DeWitt patch. Maybe these things should be called, these things deserve to be called complexities. But why do I use the word complexity and not some other word? I said, oh, this should be dual to state complexity. But what is this object? Like, what is this? What is the definition of state complexity? So in fact, it's a little bit of an embarrassment of riches, because there are too many definitions of complexities in the CFT, and none of them is particularly good for the holographic purposes. So what are these proposals? I can just list a few of them. There is a proposal coming from the Fubini study metric, or generalizations of it. So some kind of notion of distance in Hilbert space appropriately generalized. There is a notion from tensor networks. I will mention this in more detail in a moment. There is a notion, there's a proposal that involves query complexity. There is a proposal, I mean, there are lots and lots of different proposals. And so there is no consensus definition of what the word complexity should actually mean when it applies to states in a CFT. We know what it should be on the ADS side, but what is actually the CFT meaning of the state complexity? That's not clear. And in fact, it's because I just told you that, so this comment was about the not yet well-definedness of complexity on the CFT side of the duality. On the ADS side of the duality, the very fact that we have these two proposals, volume or action in the Wheeler-DeWitt patch, well, it begs the question, maybe there is a notion of complexity which is equal to volume plus the action here. Or maybe it's equal to 1/4 of this plus 3/4 of that. And in fact, because volume and action have different units, what if I had to combine them in some way, it would always come with dimensionful coefficients. The moment I have dimensionful coefficients, why can't I have some dimensionful coefficient times volume squared? Or indeed, action to the power 5/4 times volume to the power of pi. I mean, there is nothing forbidding that. And so even in the bulk, there is just a large freedom in how we would want to quantify spatial sizes of geometries. So I emphasize these two proposals because they have attracted the most interest in the literature so far, but there's nothing sacrosanct about them. And in fact, there may be other, perhaps more appropriate for some purposes, proposals or possibilities for how to, what to call complexity even on the ADS side. Okay, so given this introduction to the idea of complexity, the key thing is that it should be something about measuring spatial sizes of ADS geometries on the one hand. And then the second thing is we don't quite know how to define it, certainly not on the CFT side in any unique way, not even on the ADS side, because there are these two leading proposals and possibly many others. So it's something that we have to define first, and then we will be able to study it properly. Are there any questions about that? If there are no questions, then I'm going to say this. So having emphasized how not yet completely well-defined the notion of complexity is, let me explain my goal. My goal is to propose a fundamental framework for talking about complexity in the CFT, which is, on the one hand, flexible enough so that it can accommodate all types of sensible bulk proposals, the volume, the action, maybe other ones. But also it should be based on principled reasoning and things that we know. So what are the things that we know about holographic duality? Those were the things that I mentioned on the first slide. the Ryuta-Kayanagi proposal, the JLMS statement, which is that statement about boost generators being dual to modular Hamiltonians. Also, entanglement wedges, the idea that if you give me a density matrix, then you're also giving me in the CFT, you're also giving me an entanglement wedge on the CFT, in the ADS. So these are the things that we know about holographic duality. And I think that rather than starting from nothing or just guessing, we should be taking the things that we already know about holography to define an appropriate notion of the CFT that we'll know about holographic duality to begin with. So this is what I would call a principled approach to defining complexity in the CFT. And that's my goal. And what I want to convince you of by the end of this talk is that when you do this, you are led to an object of this type, which is a cohomology of a certain group cohomology. And I'll tell you about what the group is. The coefficients are probably real numbers which quantify actual complexities. But the conclusion of this talk will be that an appropriately defined or appropriately selected group cohomology is the thing that we should be using for talking about complexity in the CFT. Before actually delving into this, I should say one more thing, which is in case there are audience members who are not totally familiar with this subject, one more thing, which is a very important heuristic for how we think about complexity, or why Lenny Susskind and collaborators even came up with this proposal in the first place, which is, so let's look at which is tensor networks. So let's look at pure anti-de Sitter space. Let's look at an equal time slice of it. So pure anti-de Sitter space, if I'm in ADS free, then this would just be the hyperbolic disk. And I tried to draw it over here. Now, the hyperbolic disk should be, or pure ADS, should be dual to the ground state of a CFT. And now you can ask, do we have some ways of describing the ground state of a CFT, perhaps numerically? And the answer is yes, this is tensor networks. And in particular, there is a special type of tensor network called MERA, which has been very influential in the holographic community. Brian Swingle in 2009 pointed out that this tensor network looks very, very similar, if not identical, to this hyperbolic disk. Now, what is a tensor network? It's a numerical way of describing a state of interest. In this case, it would be the ground state of a conformal field theory. What is a tensor network? Every time you see a node here, you think of a tensor which has as many indices as there are legs incident to it. And every time you see a leg which connects to indices, you see an index contraction. And so this picture actually represents lots of tensors which are contracted in various ways. And you think of the free legs here at the bottom as being little local Hilbert spaces which are components of a global Hilbert space of a CFT. And the statement is that if you choose these tensors, which are represented on the diagram by vertices, if you choose them appropriately, then this is an excellent approximation to the ground state of a conformal field theory. And Vidal and others have told us how to find tensors which indeed work in just this way. And so in some sense, this tensor network captures something about the ground state of a CFT. On the other hand, if you believe that ADS CFT is true, ADS also captures something about the ground state of a CFT, clearly. And then Brian Swingle comes along and points out, actually, these things are very similar. They have a very similar structure. They have a very similar geometry. These are self-similar structures where the number of nodes here grows exponentially. Here, volumes grow exponentially as I go further away from a central point. Perhaps a space-time is a tensor network. And so it's very useful to think, even if you don't believe that statement exactly, it's very useful to think roughly that tensor networks are like toy models of gravitational spacetimes. And now this toy model is very useful for thinking about complexity, because what would you say a state complexity is of this state? You would say, oh, it's how complex it is to assemble a state from basic units. What are basic units? Maybe these basic units are the tensors themselves. And so maybe I should just count how many tensors there are. Now, if I count how many tensors there are, and then I also believe Brian Swingle's proposal that this tensor network is like a gravitational, as a spatial slice of a geometry, then counting tensors is roughly like taking the volume of this equal time slice. Now that's one more motivation for this for this volume proposal that I mentioned before. So it's very useful to think about tensor networks as a visualization tool, which explains why one would even surmise that state complexity should be related to volumes. Think of the space-time as a tensor network, and then you're just counting tensors. Now, if this was the full story, this talk would have no reason to be. We would just say, oh, that's what complexity is. But it can't be the full story, because here, even at the level of the tensor network, there's a clear complication that you can see. Now, why is this? Let's think about this index contraction. Now, when I have these two tensors being contracted in one place, nothing stops me from applying a unitary and then reverse that unitary right away, and then call the combined effect of the vertex with the unitary, call it a new vertex, and this u bar, or sorry, u dagger with the other vertex, I would call this a new second vertex, and that would look outwardly exactly the same as the contraction I had before. And so when we draw pictures like this, I can describe with them exactly the same state, but the tensors are still subject to an ambiguity, because I can put these unitaries on every line and then split the unitaries between indices, and that redefines what I mean by the vertex. And so counting vertices should somehow naturally account for this freedom. This is a gauge freedom in a tensor network, which is a tensor network version of the familiar statement that global symmetries in the CFT are local symmetries in ADS. And roughly speaking, I can think of this freedom of choosing, of entering these U's or reinserting these U's as the diffeomorphism invariance in the bulk of ADS. Now, but the presence of this gauge freedom tells us that it can't be the full story to just count tensors. We have to be doing something more clever about the tensors to define appropriate measure on the tensors, so that we can have a gauge invariant and a truly physical measure on how hard it is to assemble a state, or what the state complexity should be. And so the idea is that this cohomology is going to be that thing. Now, in the second half of my talk, I am going to tell you about a different system, which is a toy model for holography, a very simple toy model for holography, which is directly understood in terms of a cohomology. And then we will see that the relevance of the cohomology for describing this other system is exactly the same as the relevance of whatever considerations we have about holography to defining complexity. So this other system I will be telling you about is called the cluster state, and it's characterized by a symmetry-protected topological order, and which is something that condensed matter theorists care very much about. And it is also a resource state for an alternative method for doing quantum computation, which is called measurement-based quantum computation. And this is where my collaborator from UBC, Robert Ausendorf, comes in. He invented this thing. And so this cluster state is a very special state, and we will be talking about this cluster state in some detail, so that I explain to you how cohomology, the concept of group cohomology, is first of all essential to understanding the properties of the cluster state. And then we will see that understanding that is really the same as understanding how complexity should work in holographic states. And so to do this, you have to forgive me and allow me to talk about the cluster state in some detail over the next 2 or 3 slides, so that we get a picture, and then we'll be able to map it to holography again nicely. So here's what the cluster state is. I typically want cluster states on circular setup. So here's a little hexagon. There are 6 qubits. Oh, so I forgot to say, a cluster state is just a state of a bunch of qubits. The simplest case, which is enough for me to illustrate everything I want to, is a cluster state on 6 qubits. So here I drew 6 of them. And let me initialize them in the plus state. So it's the +1 eigenstate of the X polymatrix. So in the Z basis, it's this state. I take 6 of them, and then I act on them on the nearest neighbors of them with this gate, which is called the C phase gate. And in the Z basis, it would be just written like this. We also call it the C phase gate, or, well, yes, it's a C phase gate because it adds a phase to, or addresses a state with a phase depending on the state of one of the qubits. That's what this matrix really means. Okay, so this is our state. We started from a product state, and now we acted with these C phases. One thing you can see is that the C phase is not a tensor product of something that acts on one qubit and another qubit. So the C phase is going to have an effect of entangling every neighboring pair of qubits. And then I act with C phase on qubit number 1 and 2, and 2 and 3, and 3 and 4. So in the end, everything is going to be entangled with everything else. And what we want to ask is, how do I understand this cluster state in some organized fashion? Now, I just told you that it's a research state for measurement-based quantum computation. So there is something very interesting about this state, which allows you to just do quantum computations by measurements alone. Not every state can do it, this state can. So it's definitely a special state. So let's try to understand it in an organized fashion. Now, suppose that I wanted to take this cluster state, I'm going to call it phi everywhere, and I want to see what is its overlap with some basis state, which is plus, minus, plus, minus. Plus is the +1 eigenstate of x, minus is a -1 eigenstate of x. So in this product basis over the individual qubits, suppose that I want to understand it. It means that I took a cluster state that's plus, 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 plus. I applied these C phases. That's how I draw them here in this diagram. And then I want to measure the individual qubits in the plus minus basis. Yes. Now, when I do this, notice that a single unit of something repeats itself. I circled it here, and then I redrew it here. And this unit, this basic thing that repeats itself is like this. I have some state coming in from here. I have another plus state coming from the initialized pluses. I act with a C phase, and then I measure in the plus minus basis. I'm going to call this object A plus minus depending on whether the measurement actually returns a plus or a minus. Okay. And what's interesting is that the final outcome for this amplitude of that plus minus basis state in phi is a repeated version of this thing which circles on itself. And so basically I'm forming a trace of a bunch of these things, which are called these A's. Okay. So I get that, the amplitude of the plus minus whatever basis eigenstate is basis state in the cluster state, this amplitude is non-zero if and only if this combination of A plus minuses has a non-vanishing trace. And the traces tell me what the amplitude is. So this allows us to write the cluster state in this fashion. I have lots of possibilities for what pluses and minuses are, but each of them has a weight in the wave function, which is the trace of a bunch of these A's. Okay. Now, these A's, by the way, the way that we are defining these A's is something that's well known in the information theory community. I have a state coming in, a state coming out. This thing is called, but I took another plus state and I measured in a plus minus basis here. This combination of, or this basic unit of what I can do with a state is called half teleportation. And if you think about how quantum teleportation works, this is actually 1/2 of it, as in it allows you to transport 1/2 of a qubit from this place to this place. There's also one more thing that I should say, which is that we can compute what these A pluses and A minus are. So far, I have just defined them. And here there's a cheat sheet about how they are defined, but it doesn't matter terribly what they are. They're just some things that we can compute explicitly. Okay, so now I'm sorry for this slide because it's very busy, but I will tell you what to take out of it. So A plus and A minus, so two such basic units done in sequence, give me the identity. A plus and A minus give me the Z matrix. A minus A plus give me an X matrix, and A minus and A minus give me an XZ matrix. These are the Pauli matrices. Okay, and notice that now I have marked these things that can happen in the cluster state as I measure it, with 4 combinations: plus plus, plus minus, minus plus, and minus minus. These naturally correspond to elements of the group Z2 cross Z2. But how exactly do they correspond? Well, let's try if I multiply them together. For example, A minus minus times A minus minus. Now, if I got A plus plus, then I would say, oh, this is a representation of Z2 cross Z2. But I don't get A plus plus, I get minus times A plus plus, which means that I'm getting the correct group multiplication so that these A's actually form a representation of Z2 cross Z2. but only up to a phase, which can be only plus or minus 1. Now, what do we call this kind of assignment of group elements to matrices so that their matrix multiplication follows the group, but only up to a phase? We call it a projective representation. And that phase, I'm going to call it omega GH, where G and H are the two elements of this A. Now, this omega GH, if it is indeed a projective representation of Z2 cross Z2, it cannot be chosen at will, because what happens if I take 3 different A's and multiply them together? Now, because of associativity of matrix multiplication, I can think of this in 2 different ways. First, combining G and H to form 1 omega, so 1 phase times AGH. But I can also first combine H and K to get 1 phase, which comes from GH. So in the end, I have an equation which governs what these omegas can be or how they can be chosen. These omegas are just the extra phases that screw up, if you like, the matrix multiplication of this would-be group representation. And when this equation is known formally as the 2 cocycle condition. And so we would say this omega belongs to the second cohomology of Z2 cross Z2 with elements in an appropriate field. In this case, we just took plus minuses, so it kind of doesn't matter what I say, but because they're phases, it's natural to think of them as U1s. So projective representation of G is what we got by studying the cluster state. Now, it turns out that I just told you that the cluster state is characterized by symmetry-protected topological order. And symmetry-protected topological phases of matter are precisely characterized by an appropriate cohomology of a certain group. And so that's the reason why this object has shown up here. They're also classified projective representations of groups, which is what this part of the slide was telling you about. And let's see just a little more about how this 2 cocycle condition is relevant for the cluster state, and then we will right away map it to the holographic question. So, maybe a comment about why this is called a 2 cocycle. So imagine a tetrahedron and map and mark edges of the tetrahedron with elements of Z2 cross Z2. And now the statement that think of this omega as a flux that comes through a side of this tetrahedron, which is marked by, say, G and H, or GH and K. The statement that this 2 cocycle condition, which is this equation, is a statement that the flux in through these two sides of the tetrahedron is the same as the flux out through the other 2 sides of the tetrahedron. And when I have flux in equals flux out, that means that there is no source inside the tetrahedron. And so the setup is described by, if you like, a harmonic function. In this case, it's a harmonic function over simplices of G elements. And so that's the reason why this omega deserves to be called a cohomology element or a cocycle. In this case, it's a cocycle for the cluster state. It's a cocycle of Z2 cross Z2 with coefficients in U1. Now, we need one more thing about the cluster state, which is useful before we can jump back to holography, which is that it can be prepared, the cluster state, it can be prepared by a topological field theory whose action is actually given just by this cocycle. So I have an equation here where the exponential of I times the action is this combination of the cocycle elements here. Now, why is that true? I have a little calculation here, and maybe 2 slides ago, I had an equation of just this type for what the cluster state is. And then I'm just going to repeatedly apply the projective representation definition of A. And then eventually I get to this statement. And now this here is just e to the is from the box. And so that's the reason why this state is really a Hartle-Hawking state of this topological field theory, where these coefficients are exponentials of I times the action. Okay, and you might say, why was it important that I drew these omegas from the cohomology? Why did they have to be cocycles? Well, here is a state on 3 legs. Here is also a state of 3 legs, but triangulated differently. And the statement is that the fact that the omega is a cocycle means that the state is the same independently of the triangulation. And so triangulation independence, from the point of view of this topological field theory that prepares the state, is the content of the cocycle condition. So now we're back to holography. And I just told you that for the cluster state, what was important about the 2 cocycle is that I could prepare it by a path integral over a certain set of triangles. And then independently of the triangulation, I would end up with the same state. And what's that independence of triangulation? It's the 2 cocycle condition. So now we want to make literally the same statements in the context of holography. Here is a piece of a holographic state in spacetime, an equal time slice. And I want to draw this to take this equal time slice and triangulate it. So dual to a triangulation is a network with trivalent vertices. Okay, so here is a picture of an equal time slice of a holographic geometry. And the statement is this, or a question that you can ponder is this. What is a state on the red lines, the ones that I have marked here? This is a well-defined holographic question. I have a certain cutoff surface which defines a state for me at this cutoff, and I can ask what is the complexity of that state. And now, if this was a topological field theory, then I would say, oh, I'm just going to count these triangles. In the case at hand, we have really a conformal field theory which prepares this geometric state at all different scales at the same time. There is a lot of debate in holography about what we mean by putting a cutoff at a particular location in the bulk, but we can be, so this is definitely not a clear-cut statement, but let's be brave and let's just take at face value the statements that we have seen from before. Lenny Susskind told us that complexity is like the action that prepares this state. And then when we looked at the cluster state, the action was just like a cocycle taken from an appropriate group. So maybe I can combine these 2 statements and say that complexity is like a cocycle. That's indeed the statement that I want to convey to you. Now, the importance of the concept of cocycle was that this thing had to be independent of triangulation. So far, I just sort of made 2 leaps. I took a piece of wisdom from Lenny Susskind, which was very qualitative. Then I took this completely different toy model, which is not similar, but not the same as a holographic system. And I took a statement that's valid there. And I want to make a proposal based on these 2 combined connections. But what is the basis for it other than these qualitative statements? The key thing is about the importance of the cocycle condition. So in the context of the cluster state, the cocycle condition was that it could be prepared by a topological field theory independently of triangulation in the manifold, on how we triangulate the manifold that prepares the state. But what is the statement in holography that I hope to achieve from the cocycle condition? And the statement is that I want to achieve independence of RG scheme in the bulk of ADS. Perhaps it's not everyone remembers from the audience that radial direction in ADS corresponds to the RG direction in the CFT, changes of scales. And so I want to say that the cocycle condition, as we apply it in holography, is going to produce for me an independence of the notion of complexity from how we do RG at intermediate scales. So here's a picture of how this is going to work. Here's a picture of local RG. Suppose that I have a state in the CFT. You can think of this as a tensor network, or you can think of this maybe more loosely. It's a state that locally is a state on 4 different subregions, A, B, C, and D. And now I took these 2 triangles. Okay, this state is defined using trivalent vertices. So its dual consists of triangles. And this is where the cohomology is going to be nicely applied. And now I took 2 neighboring triangles, and I want to take this square and I want to retriangulate it in a different way. If I assign numbers to these triangles using the cocycle, then the 2 cocycle condition guarantees for me that the sum of whatever numbers I have over the green triangles is equal to the sum over the red and the blue triangle. How do I understand the green triangles? These are the state complexities of these state. But how do I understand the red and the blue one? Well, here I made something like you can call it crossing symmetry or something. I retriangulated a square. So now I end up with a state which is on a strictly coarser cutoff. Here I had A, B, C, D component Hilbert spaces. Now I have A and D like before, but B and C have combined to a single Hilbert space that's over here. And so my new state is only defined here, and the red triangle is the only one that contributes to the complexity of the state, whereas the blue one is not a part of the complexity of the state anymore. It's how inputs or Hilbert spaces have merged together and coarsened to a more coarser Hilbert space. What do we call this thing? We call it RG, when I take two Hilbert spaces and replace it with one effective one. And so I see that the co-cycle is going to apply for me, is going to assign a number to this triangle, which combines the BC Hilbert spaces to one effective Hilbert space. This is an RG, this is the complexity cost of doing RG. Notice that this is very similar to what Mera was doing, or our tensor network was doing. Here too, I was combining Hilbert spaces into successively smaller Hilbert spaces. And if I wanted to count complexity by counting tensors, I would have to assign some number to this tensor, which takes two Hilbert spaces and maps it into one. That's exactly what happens in this blue triangle here, over here. But there were no rules other than just counting tensors before. Now there are rules. The rules are take an object from an appropriate cohomology, which assigns numbers to these triangles that combine Hilbert spaces and coarsen them, and that is that's how complexity should really be counted. And the two co-cycle condition, I just remind you, is the statement that if I do my RG in different ways, maybe I first combine Hilbert spaces and then I have a coarser state, or I never combine Hilbert spaces, but then I have a state at a finer cutoff. In the end, the complexities end up, add up. So they agree regardless of my internal RG scheme. Now, I promised that cohomology is going to give us a notion of complexity with the right heuristics. And I think that the previous slide gives us the right heuristics and with rules, okay? So you only have one more question to ask me, which is what is this group that I'm talking about here? For the cluster state, it was Z2 cross Z2, but what is the group in the context of holography? And the statement is that maybe here, every time I have a line here, I think of this line as being a piece of an Ryuta-Kayanagi surface. So every time I have a state defined at some variable cutoff, I can always think of entanglement wedges, which are just tangent to the cutoff surface. And if I start with this as my basic object, then it is natural to take the group which maps any density matrix to any density matrix. It's clear that if I consider density matrices which have the same degeneracy spectrum, so if I don't ever do level crossing, then there is a group which maps any density matrix to any density matrix. There are clearly inverses in this operation, and this operation is clearly associative. And so there's always a group which whose representation are the density matrices. That's how I should put it. And then any such group, if I take the cohomology of that group, that is going to give me a natural notion of complexity for holography. Now, I don't have much more time to talk about how to talk about this or how to define this group generally, but here's an example which is taken from the ground state of a CFT. So if I take a ground state of a CFT, then I can ask, well, what can I do with density matrices just drawn from the ground state? Well, here is one density matrix where the left endpoint is L and R. It defines for me some entanglement wedge, and there is some region, some interval in the CFT. And then I can map it to any other interval in the CFT if I'm in the ground state, to any other one which has endpoints L prime and R prime through the action of L-1, L0, and L+1. And so in the case of the ground state of the CFT, the group that I need to invoke for my cohomology is SL2R, because SL2R allows me to map any density matrix to any other density matrix. So that's just what I wanted to do over here. Any density matrix to any other density matrix must be mappable using that group. If I'm in the ground state, that group is just SL2R. And to talk about if you remember how the tetrahedron worked, okay, for the cohomology, I always had a rule that one edge and another wedge for a third edge that closes a triangle had to be the product of these two group elements. We were assigning group elements to edges, and then the third edge of any triangle was the product of the other two. Now, what this means is that basically the group cohomology is something that applies naturally to situations where I have a flat G connection. And so here I have this SL2R group, evidently, which is relevant for describing complexity of the ground state. Now, have we ever seen a situation where there is a flat SL2R connection? And the answer is yes. That's the Chern-Simons description of ADS-free gravity. And so a very special case or application of the general formalism that I'm proposing here is to take the group cohomology of SL2R and define from that different notions of complexity for the ground state of the CFD. It turns out that that job was actually already done in a project that I have done together with Wang Zizhi and with Chen Bo and with my students a year ago. And we constructed exactly these two notions of complexity that the cohomology allows us, but we didn't know that we were talking about cohomology. So our paper was written in a very roundabout way. But when we re-examine it from the current modern cohomology perspective, you recognize right away that the thing that we were actually defining in that earlier work was actually the cohomology of SL2R. And my proposal is that if you take the group G that maps transitively any density matrix to another density matrix, that gives you basically the full set of possibilities for how complexity can be defined, subject to a single physical input, which is that it shouldn't matter how you do your RG, your complexity should be the same. Okay, that's everything I have. Thank you very much.
Thank you very much, Bartek. That was really interesting. So there's probably time for a quick question if anyone has anything pressing to ask.
Hi, Bartek. I have one about higher dimension. How do you generalize this group cohomology concept to the higher dimension?
Yeah, so because it's cohomology, I've been putting H2 because I was mostly thinking about ADS free and equal time slice geometries of there. And so it's natural to guess that you're just going to replace the subscript here with a higher dimensional cohomology in higher dimensions. But I would lie if I said that I understand this fully. There are some things about higher dimensions that I don't yet understand, and this is the subject of the ongoing project. So that's why this work is not out yet. I think I understand the situation maybe as free, but I'm not sure if I understand. I'm not sure, but I don't yet understand it in higher dimensions. But cohomology is such a flexible concept, and sort of not. It's not hard to dimension. It's natural to define it for higher dimensions and higher dimensional simplices. So I think it should work there, but I'm not yet sure.
Okay. And I have a second question. How about mixed state? I said excited state. So sorry.
Can you say again? How about which state?
Excited state. Now you say the complexity of the factual state is belong to the cohomology, but if I consider excited state.
Oh no. Oh yeah. I should stress this. So what I meant by this slide states my general proposal, which is that I will always take a group which maps transitively any entanglement wedge or any density matrix to any density matrix. And that statement should be true regardless of whether you're talking about a ground state or an excited state. Okay. So the proposal is meant to be general. But this group here is very intractable in general. And so you might say, is there any special case where I can do actual calculations, where this group is a little easier to handle than just defining it formally with this box? And so I say, in the ground state, we can do it. Because in the ground state, I don't need a large group. The group is just SL2R. And so I know exactly what I'm talking about and everything is calculable. Whereas when I'm not in the ground state, this group, it's not SL2R, but some larger group that maps arbitrary entanglement wedges to one another. And so there we don't know how to calculate it. I mean, we don't know how to do calculation.
Thank you.
The proposal should be true. It's just we don't know how to calculate.
Okay, excellent. So thank you again, Bartek, for a lovely talk. I think that's
Thank you so much.
Yeah, brilliant. So I think we'll move on to our last talk of the session.